Welcome back to Nature Documentary for Sleep. If you enjoy calm geography, leave a comment and consider liking and subscribing. Tonight you're stepping onto the Andes Altiplano, a plain that sits up in the sky. It's pre-dawn near Lake Titicaca, and every breath is thin, cold, and slightly work-related. You stand on ground that's flatter than it has any right to be, at an altitude where most landscapes choose drama. To the east, the Cordillera Real holds a jagged line, and to the west, the volcanic arc keeps its distance. Between them is the Trick, a wide interior basin lifted thousands of meters without becoming only peaks. You can hear the planet's method in the silence, compression at the coast translated into thickness inland. And because this surface rose, winds were rerouted, rain was rationed, and lakes learned to end without an ocean. So what specific chain of subduction angle, crustal shortening, and lithospheric root failure lets a whole plateau rise and stay broad? A reed bed rustles at the shoreline, and it sounds like paper being slowly torn. A distant truck downshifts on a road you cannot see, and the engine coughs in the cold. Your lungs answer with their own opinion, a dry little protest that says, "You are not built for this." You think the danger here is dramatic, like a cliff or a crevasse. Wrong. The first threat is invisible, and it is already inside you, because altitude is a tax with no refunds. You take another breath, and the air feels unfinished, like it forgot to include enough oxygen. And that is your first piece of evidence. This plane is not just high, it is persistently high. High enough to make ordinary tasks feel negotiable. If the plateau rose only as sharp peaks, you could step down again quickly. But here, the flat goes on, and the flat keeps you up here until your body agrees to run a different program. So you make a decision, because you need a way to read a landscape that looks deceptively simple. You stop looking at the ground, and you start tracing the walls. You let your eyes follow the Cordillera Real eastward, where glaciated ridges hold on to the last blue shade of night. Then you swing your gaze west toward the volcanic arc, where cones and calderas sit like closed mouths. The plateau is the space between those teeth, and the teeth tell you the pressure came from somewhere else. A thin line of pink appears behind the eastern mountains, and the lake takes it personally. For a moment, Lake Titicaca looks warm, almost welcoming, but the cold stays in your hands, and the wind stays indifferent. You crouch and drag your fingers across the soil near the shore. It is not beach sand, it is finer, darker, and it smells faintly of minerals that have been rinsed and re-rinsed. This is not a place where rivers rush away to the sea. This is a place that keeps its sediments like a desk drawer that never gets cleaned. That retention is not a vibe, it is a tectonic consequence. Because when a region becomes an interior basin, it starts collecting time. A gull calls, and the sound skates across the flat water, then vanishes. You stand up slowly, not for drama, but because standing up quickly is how you learn the hard way about thin air. Your head gives you a gentle, unhelpful lightness. Congratulations. Your brain is now budgeting oxygen like it is paying rent. And while you are doing that, the plateau does what it always does, which is sit here and pretend it is normal. But you did not come to accept the tourist version. You came for the mechanical version. So you begin walking, not far, just enough to feel how the ground changes under your boots. The surface is flat, but it is not uniform. There are slight swells, low ridges, shallow depressions, the kind of topography you get when a basin fills and settles and fills again. You notice a line of stones arranged into a crude wall, an old boundary, maybe for animals. On this plateau, humans become obsessive about boundaries. Not because they love fences, because water is rare, warmth is rare, and a level patch of ground that will grow anything is rarest of all. Every small advantage here is fought over politely, then forever. The sun finally breaks the ridge, and light spills across the plain like a slow flood. It reveals something else you could not see in the dark. Farther out, beyond the reed beds, the land is not just flat, it is wide. Wide enough that the horizon feels like it has been stretched, and that width is the puzzle. Mountain building usually makes peaks. Here, mountain building made a table, so the escalation arrives, concrete and unavoidable. If you cannot explain how the table got lifted, then you cannot explain why this lake still exists up here. You cannot explain why there are salt flats farther south, where water dies and leaves its minerals behind. You cannot explain why roads crack, why towns settle unevenly, why earthquakes arrive like surprise bills, and you cannot explain why the air itself feels like a personal insult. You turn your body west toward a brightness that is not just sunrise. It is reflected light off ice far away, and off pale volcanic ash, and off a sky that feels closer than it should. And you start imagining the coast, not because you can see it, because everything that happened here began there. You picture the Pacific margin as a long, wet blade. You picture waves folding and breaking, the normal chaos of water. Then you picture what the water hides, a trench offshore, dark and deep, where the seafloor bends down like a tired spine. Out there, the Nazca Plate is still moving, still sliding under South America. Not fast, not loud, but with the patience of a conveyor belt in a factory that never shuts down. Here on the Altiplano, you can feel that motion only as a consequence. A plateau does not rise because it wants to be scenic. It rises because the margin is being crumpled, and the crumpling has to go somewhere. You keep walking, and the thin air forces you into a slower cadence. That slower cadence helps because geology is not in a hurry. You pass a patch of toda reeds, tall and stiff, their bases rooted in shallow water. They look soft from a distance. Up close, they are hard, fibrous, practical. This is a plant that learned to live with cold nights, intense sun, and a shoreline that shifts like a mood. That shoreline shift is another clue. Lake Titicaca is large, but it is not a simple bowl of water. It breathes with seasons. It remembers wetter periods. It carries the faint signature of being part of something bigger, an older system of lakes and wetlands that expanded and contracted across the plateau. That kind of hydrology belongs to basins that do not drain. So you look for the missing piece, the absent river that should be cutting an escape route, and you do not find it. Instead, you find a quiet arrogance in the landscape, as if the plateau assumes it can keep its water. That assumption is only valid if the rims are high and if the interior keeps rising with them. Now the story has to move, because staying here too long will make this just a cold morning by a lake. You need to follow the force back to its origin, but you cannot simply walk to the coast. It is too far, and your lungs have filed a complaint. So you do the thing explorers do when distance is unreasonable. You travel with your mind and with the evidence in front of you. You pick up a small stone from the ground. It is rounded, smoothed by transport, not fresh from a cliff. This stone has been moved by water, maybe by streams that once ran stronger than they do now. You roll it between your fingers, feeling its weight. It is ordinary. That is the point. Ordinary stones at extraordinary altitude means this surface used to be lower, or the transport used to be more powerful, or both. And because the simplest answer is rarely the correct one, you prepare for the complicated truth. The complicated truth begins at the trench, where oceanic crust does not politely disappear. It arrives soaked. It arrives cracked. It arrives loaded with seawater, trapped in minerals, in pores, in the very fabric of the rock. As it slides beneath the continent, that water gets squeezed out, not all at once, but in stages. And when water enters hot rock under pressure, it changes everything. It lowers melting points. It makes the mantle above the slab behave differently. It helps feed volcanoes. It helps lubricate faults sometimes, until it does the opposite and locks them. That is the first mechanical link. Subduction is not just pushing. It is also chemistry. It is also plumbing. And that plumbing eventually expresses itself here, on this high plain, in the form of volcanoes to the west, and a thickened crust beneath your feet. But you are not there yet. You are still standing by a lake that looks peaceful enough to sell postcards. So you force another development, another step in the chain. You turn away from the water and look upslope toward the east, where the Cordillera Reel rises sharply. Those peaks are not decorative. They are a wall that wrings moisture from air coming in from the Amazon. That means the eastern flank is wetter, more eroded, more cut by rivers. The interior is drier, more preserved, more likely to stay flat once it is filled with sediment. So, climate is not an afterthought. Climate is part of the construction crew. You walk toward a small outcrop of exposed rock where the soil is thinner. You kneel again, and this time you touch the rock itself. It is cold, and it feels dense, and it has a faint sheen where it has fractured. In your mind, you place it in a stack, because that is what this entire plateau is. A stack. The crust here is thick, thicker than normal continental crust, not because someone poured extra crust into a mold, because the continent was shortened, compressed, folded, and shoved over itself, like books forced into a shelf that is suddenly too narrow. Some books tilt, some break, some slide over others. The shelf bulges. That bulge is altitude. And now you are close enough to the core question to make it hurt a little. If compression thickens crust, why is the surface not just jagged mountains everywhere? Why do you get this broad, high basin instead? The answer is uncomfortable. The answer is that rock can flow if you give it heat, time, and enough pressure. Deep in the crust, below the brittle layer where earthquakes happen, rocks deform like very slow caramel. They fold without snapping. They squeeze sideways. They move in ways your surface brain hates to imagine. So as the Andes thickened, the deep crust warmed. Some of that warmth came from burial. Some came from radioactive decay. Some came from magma moving up from the subduction system. And as the deep crust warmed, it began to behave less like stacked bricks and more like a heavy paste. That paste can smooth topography from below. It can help create a plateau surface, broad instead of needle sharp. You stand and you feel a brief dizziness again. Not dramatic, just enough to remind you this place is not friendly. You take a slower breath. You watch the sun climb. The lake brightens. The reeds cast thin shadows. And beyond all that beauty is a grim practical fact. If the plateau surface is preserved, it is because erosion here is limited. And erosion is limited because moisture is limited. And moisture is limited because the mountains rose and stole the rain. So the plateau is self-reinforcing. Uplift makes walls. Walls make rain shadows. Rain shadows reduce erosion. Reduced erosion helps maintain high elevation. That is not poetry. That is a feedback loop. And it does not care if you are impressed. Another sound drifts across the plain. Faint, but distinct. A dog barking in a village you cannot see. It is a small sound, but it brings humans into the frame. Humans live here because humans will live anywhere that has a water source and a flat place to build. They grow quinoa. They herd llamas and alpacas. They build with adobe that dries quickly in the dry air, then cracks when the wet season remembers itself. And everything they do is a negotiation with altitude and dryness. They plan their days around cold nights. They plan their crops around frost. They plan their bodies around thin air. So the stakes are not abstract. The stakes are lungs and harvests. And whether the lake level drops enough to ruin a shoreline garden, you look down at your hands, slightly dry already, skin pulling tight. Even your body is being eroded, and that makes the next decision feel necessary. You need to go west, at least in the story, toward the margin where the compression begins. Because until you picture that trench, until you feel the slab angle in your mind, the Altiplano will remain a trick with no explanation. So you choose. You choose to leave the comfort of the lake behind, and you choose to follow the cause back to its source. In your imagination, you descend. You travel down the western slope of the plateau, where the air thickens slightly and the landscape changes. The flat breaks into basins and ridges. The ground becomes dustier. The vegetation thins. You pass through towns that cling to water channels like they are life support, because they are. And then you reach the western Cordillera, where volcanoes start to appear more regularly. They rise out of the plain like blunt promises. Some have snow caps that look clean from a distance and filthy up close, streaked with ash. Some are old and eroded. Some are young enough to still look sharp. They are a reminder that subduction is not only compression, it is also melting. And melting needs a pathway to the surface. You pause there, because this is a revealing moment. The volcanoes mark the line where fluids from the slab trigger melting in the mantle wedge. They are the surface expression of a process happening far below. And they sit on the west side of the plateau, helping define the rim. A rim that keeps water from escaping. A rim that keeps the interior trapped. a rim that keeps the plateau behaving like a bowl. Now you push farther west in your mind, beyond the volcanoes, across the forearc. The forearc is a region that feels like it is holding its breath. Not as high as the plateau, not as wet as the eastern flank. It is caught between the trench and the high Andes, squeezed, scraped, and slowly rearranged. And then you reach the ocean, you stand on a cliff above the Pacific, and the air is suddenly heavy with salt. Waves slam the rocks below, white and loud, performing their daily demolition. It sounds powerful, like this is the main event, but you know better now. The real violence is quieter, and it happens where the seafloor bends and disappears. Out there is the Peru-Chile Trench, a long scar in the ocean where the Nazca Plate dives beneath South America. You watch the surface water churn, you watch seabirds circle, and you picture the slab going down at an angle, dragging its soaked minerals into higher pressures and temperatures. At first, it is a clean descent, the way you might imagine a slide, but it is not clean. The top of the slab scrapes sediment off the ocean floor and smears it onto the margin. The interface between plates locks and slips. Earthquakes happen not as random events, but as episodes of stored strain being released. When the interface locks, the continent is pulled, bent, and stressed. When it slips, the stored energy releases, and the coast jumps. And inland, far from this noise, the plateau remembers the compression as slow thickening. You lean into the wind on the cliff, and it smells like kelp and wet stone. You can almost forget the Altiplano up there, because this feels like a different planet. But then you make the connection explicit, because the story depends on it. Every millimeter the Nazca Plate moves under the continent is a millimeter of potential shortening. Not all of it becomes mountains. Not all of it becomes earthquakes. Some of it becomes heat. Some of it becomes magma. Some of it becomes a subtle push that migrates deformation inland. And here is the next reveal, the one that makes the Altiplano possible. The angle of subduction is not constant. Sometimes the slab dives steeply. Sometimes it goes shallow, flattening under the continent like a hand sliding under a rug. When it flattens, the whole system changes, and you feel it far inland. Because a shallow slab does not just dive and vanish, it scrapes along the underside of the continent, wide and stubborn. It turns the margin into a long clamp, spreading pressure over a broader zone. You think of pressure as a point, like a thumb. Wrong. This is a forearm across a tabletop, pushing everything inboard. So you stand on the windy coast, and you imagine that invisible forearm reaching under you. You picture the Nazca Plate gliding beneath South America, not politely, not cleanly. It is a rough conveyor belt, dragging hydrated crust down into heat. And as it drags, it leaks. Not water like a dripping pipe, but water forced out of minerals. A slow squeeze, a deep dehydration, a chemical confession. That water rises into the mantle wedge above the slab. It lowers the melting temperature, the way salt makes ice give up. And melt is buoyant, and buoyant things climb. This is why volcanoes line up like receipts along the western Andes. But the bigger consequence is quieter. A shallow slab changes where the crust breaks. It shifts deformation inland, away from the trench, into the continent's interior, you can almost watch it happen, like stress migrating across a body. The coast tightens, the forearc stiffens, and the squeeze walks eastward. So you make a decision. Because your mind needs a route to follow. You follow the slab by depth, not by distance. You imagine it descending, and you track the events like stations on a night train. Near the surface, the plate interface locks, and earthquakes happen when it slips. Farther down, minerals lose water, and the mantle starts to melt. Farther still, the slab heats and transforms, becoming denser, less itself. And all the while, the continent above is being shortened, thickened, and rearranged. That thickening is the hidden engine of the Altiplano. Not the peaks, not the volcanoes, not the postcard, the thickness, because thick crust is buoyant like a foam mattress forced into a corner. If you shove it hard enough, it cannot go sideways forever. It starts to bulge upward, and unlike a single mountain, a thickened region can lift wide. That is how you get a plane in the sky. You watch the Pacific surface flash in the sunlight. It looks carefree, almost smug. But below that shine is the trench, and below that trench is the grind. And now you need evidence, because this cannot be only metaphor. So you bring your attention back to the Andes, to what rocks and waves can prove. Along the margin, you find uplifted marine terraces, old shorelines stranded above modern waves. Like the ocean forgot them, they tell you the coast has been rising in steps, not continuously, but in jolts tied to earthquake cycles. Inland, you find folded sediments, faulted basins, mountain fronts that look like bruises. This is a continent under compression, recorded in its posture. You take that posture and stretch it across a cross-section in your mind. The trench to the west, the volcanic arc farther inland, then the high plateau, boxed between mountain belts. And you realize the plateau is not centered on the trench. It is offset, like the deformation chose a different address. That is the signature of shifting slab geometry. So you stop pretending subduction is one simple angle. You treat it like a living hinge. Slab angle changes over millions of years for reasons that are both boring and terrifying. The age of the oceanic plate matters. Older plates are colder, denser, and they sink steeply. Younger plates are warmer, more buoyant, and they resist diving. Seafloor features matter too, like ridges and plateaus. When thickened oceanic crust arrives at the trench, it can jam the descent. It is like trying to shove a loaded suitcase under a bed. The slab flattens, the interface grows longer, and the continent feels the shove farther inland. And when the shove goes inland, the mountains do too, not just at the edge, but deep in the interior. That is how you begin making an altiplano. But there is a cost to flattening. A shallow slab cools the mantle wedge above it. Less hot mantle means less melt. Volcanism can shut down in some segments, then restart elsewhere. So the volcanic arc can migrate like a fever moving through a body. That migration leaves clues, chains of old volcanoes, then newer ones, stepping across the landscape. You do not need to see them right now. You only need to accept the idea that the interior is not passive. It is being remodeled by changes at the margin. You lean back from the coastal cliff. Salt air fills your nose, and your skin feels damp. and you remember the dry cold of the plateau. Same continent, same plate boundary, totally different punishment. So you begin moving inland again, because this section of the story is not about waves. It is about how a continent turns pressure into altitude. You travel east, not as a tourist, but as a stress wave. First you cross the forearc, where rocks are scraped, fractured, and often dry. Then you rise into the western Cordillera, where volcanoes stand guard. Then you drop into the plateau, where the air thins and time collects. As you climb, your body returns to its earlier complaint. Your lungs tighten. Your sleepiness becomes heavier, like a blanket soaked in cold water. Congratulations. You are back at an elevation where thinking costs extra. But this time, you are not staring at flatness with confusion. You are staring at it like it is evidence in a case. So you start building the case layer by layer. A plateau cannot exist without crustal shortening. Shortening means the distance across the continent gets smaller, but rock does not vanish. So when the crust is squeezed, it thickens. And when it thickens, it rises. This sounds simple, which is how you know it hides cruelty. Because shortening does not happen evenly. It happens through faults, folds, and the kind of slow violence that makes maps nervous. You imagine the crust as a stack of stiff pages. Push from the west, and the pages buckle. Some crumple into folds. Some tear along thrust faults, one slab riding over another. That is how mountain belts grow, by stacking. And stacking is the key word, because stacking creates thickness. Now you need to choose where to stand to see it. So, you place yourself not on the surface, but inside a cross-section again. You stand in your mind beneath the plateau, looking sideways through the earth. Above you, the surface is flat and cold. Below you, the crust is thickened, like bread dough kneaded and folded. And beneath that crust is mantle, hotter, denser, always waiting. In a normal continent, the crust might be a modest layer. Here, it becomes extravagant. It grows so thick that its base is pushed into temperatures where rock stops being brittle. Down there, it does not crack the way a cliff face cracks. It flows, it creeps, it oozes over geologic time, like wax left near a radiator. That flow is what helps turn jagged relief into broad elevation. The plateau is not only lifted, it is also smoothed from within. So you look for signs at the surface that the deep crust has been behaving strangely. You find high-grade metamorphic rocks exposed in some parts of the Andes. Rocks that were cooked and squeezed deep below, now sitting in daylight. That tells you material has been exhumed, brought up by uplift and erosion. You also find basins filled with thick sediment piles. Not thin layers, but serious accumulations, like the earth has been hoarding sand. That tells you the basins were subsiding, making room, while mountains rose nearby, shedding debris. And when you combine those facts, the picture sharpens. The plateau is not one block shoved upward. It is a region that thickened, sagged in places, filled with sediment, then lifted again. A complicated rise with a lot of internal bookkeeping. Speaking of bookkeeping, you notice something else on the Altiplano. The surface often looks deceptively gentle, but rivers here do not behave like rivers in wetter worlds. They are intermittent, sometimes flashy, sometimes absent. They carry sediment when storms happen, then go quiet. That is how you build flatness, by filling low spots faster than you can cut new ones. So tectonics makes the space, and climate decides what gets stored. But you cannot talk about storage until you talk about walls. Because the plateau is not open, it is trapped between two belts. To the east, the eastern Cordillera rises, wetter and more dissected. To the west, the volcanic arc and western Cordillera stand higher, more arid, more ash-colored. Between them lies the Altiplano, an interior basin that was lifted but also contained. Containment is everything. If the region had been open to the sea, rivers would have carved deep outlets. They would have drained the basins, lowered lake levels, and increased erosion. Instead, the rims rose with the interior. The basins stayed internal, and water learned to end in evaporation. That is why salt pans exist here, why lakes turn brackish, why minerals accumulate. It is the landscape keeping its own losses on record. Now you push deeper into the mechanical reality. Crustal shortening in the Andes is distributed across many structures. There are fold and thrust belts where layers are crumpled and stacked. There are big thrust faults where older rocks ride over younger ones. There are zones where the crust is sheared, where different blocks slide past each other. If you could watch from above over 10 million years, you would see the continent wrinkle. Not one wrinkle, but many, forming and dying and shifting. This is not a clean mountain range. It is a construction site with no foreman. And somehow, out of that chaos, you get a broad, high surface. So you ask the next question, the one that keeps you awake even up here. What keeps the plateau broad instead of turning into endless, jagged relief? The answer has two parts, and neither is comforting. The first part is internal flow. As crust thickens, it heats and weakens at depth. Weak, deep crust can spread laterally. It can move from thick areas to thinner areas, redistributing mass. That spreading reduces sharp topography, raising low regions and lowering extremes. It is like a heavy cake batter settling in a pan. The second part is sediment. Basins inside the plateau collect debris from surrounding highs. Over time, they fill, leveling the surface. So even if tectonics creates roughness, the basin fills it in. A plateau is not born flat. It is flattened by processes that prefer laziness. Gravity loves laziness. So does sediment. So does warm rock. But there is a problem. Thickening crust has a limit. If you keep stacking and heating, the deep root can become unstable. Not immediately, not dramatically, but inevitably. The crust becomes too thick, too hot, and in places, too dense. It begins to behave like a structure that is overbuilt. It starts to sag under its own ambition, and that is where the story is going, but not yet. First, you need to see how thickness is built in the first place. So you walk in your mind along the front of the eastern Cordillera. You picture foothills that look tame from afar. Up close, they are folded strata, tilted layers, ridgelines made of resistant rock. Each fold is a record of compression. Each thrust fault is a place where the crust shortened by stacking. If you could peel back the soil, you would see layers that used to be horizontal. Now they are angled, sometimes vertical, like books knocked over. That is shortening made visible. And shortening is not subtle. It is the reason a continent can gain elevation without gaining material. Now, you bring in another kind of evidence, because the surface only tells part of it. Seismology. Earthquakes are not just disasters. They are signals, like the Earth tapping on its own walls. Seismic waves travel differently through thick crust than thin crust. They slow, they refract, they echo in patterns that reveal depth. Under the Altiplano, seismic studies show a thick crust, a deep root, not a little extra thickness, a serious keel, pushing down into the mantle. And that keel is why the plateau can sit high. A thick crust is buoyant, like an iceberg. Most of an iceberg is hidden. Most of the plateau's structure is hidden too. You stand on the surface and feel flatness. Below you is a deep root, and it is doing the real work. But buoyancy is not the only force. There is also isostasy, the balancing act of the lithosphere floating on the mantle. Isostasy sounds like a fancy dessert. It is actually the Earth trying to keep its books balanced. Thicker crust floats higher. Remove weight from the top, and the crust rises. Add weight, and it sinks. On the Altiplano, both happen at once. Sediment fills basins, adding weight locally. Erosion strips mountains, removing weight at the margins. And the crust responds, slowly, by adjusting its elevation. So uplift is not a one-time event. It is a constant negotiation between mass and buoyancy. Now you let the imagination zoom out. From the plateau, the Andes are not just a line of peaks. They are a wide origin, a broad zone of deformation. The mountain building affects hundreds of kilometers, not just a ridge crest. That width is important because a plateau needs width. If deformation were narrow, you would get sharp mountains and deep valleys. Here, deformation has been spread, allowing a wide region to thicken. So you start seeing the plateau as the product of distributed shortening. Not a simple uplift, but a regional thickening. And with time, that regional thickening becomes a new kind of landform. A high, plain, trapped between belts. Now you feel the need for a reality check, because it is too easy to admire this. So you think about what thick crust means for everything living on top. It means low oxygen, always. It means high ultraviolet radiation, because there is less atmosphere above you. It means big temperature swings, hot sun by day, sharp freezing by night. It means water boils at a lower temperature, which is a petty inconvenience until it is not. It means your body works harder for less reward. And it means agriculture becomes an act of stubbornness. Humans responded the way humans always do. They domesticated camelids, they bred potatoes, they learned to store food. They built on flat ground, because flat ground is precious here. And they developed cultures that treat altitude as normal, because adaptation is cheaper than escape. But the plateau is still indifferent. It does not care if you have rituals, or roads, or laws. It only cares about thickness and balance is not stable, because as the crust thickens, it becomes gravitationally unstable. It wants to spread. It wants to collapse outward, even while compression keeps pushing. This is the contradiction at the heart of the plateau. Compression builds it, gravity tries to undo it, and in the middle, the deep crust flows to accommodate both. You could call it elegant. You could also call it exhausting. Now you turn the story toward the next major pivot. A thickened plateau does not just sit there. It changes the atmosphere above it. It rewires the wind and rain patterns, and those patterns decide whether erosion keeps up with uplift. So, you start paying attention to air. Not the thin air in your lungs, but the moving air that carries water. Moisture mostly arrives from the east, from the Amazon basin. Warm, wet air rises against the eastern Cordillera. As it climbs, it cools and water condenses. Clouds build fast in the afternoons, swelling and darkening. Rain falls hard, sometimes with hail, sometimes with thunder that bounces off ridges. This is orographic precipitation, which is a polite term for air being forced to pay its water bill. On the eastern flank, rivers are aggressive. They cut valleys, trigger landslides, and eat the mountains as quickly as mountains can rise. And as they eat, they remove weight. Remove weight from a mountain range, and the crust can rebound upward. So, erosion is not only destruction, it is also uplift. Indirectly, that is an uncomfortable thought. The mountains rise partly because they are being destroyed. Now the air crosses the crest. It descends into the interior, warming and drying. The clouds thin, the rain weakens, and the plateau becomes a rain shadow, a dry interior, a place where water arrives in smaller quantities, less often, and leaves mostly by evaporation. That dryness slows erosion on the plateau surface. It preserves the broad elevation that tectonics created. So climate becomes a partner, not just a spectator, and the plateau makes that partnership stronger by being high. High land forces air to rise. Rising air drops rain on the windward side. That rain carves deep valleys there, enhancing relief at the margins. Meanwhile, the leeward side stays dry, keeping the interior intact. This is how the Andes turns itself into a climate machine. You stand on the plateau again and imagine the moisture trying to cross. It is a caravan of vapor, arriving hopeful, leaving disappointed. And the disappointment is recorded in the lakes. Because on a plateau with internal drainage, lakes are the punctuation marks. Water collects in basins. It has nowhere to go, so it waits. Then it evaporates, leaving salts behind. Over thousands of years, those salts accumulate. Over tens of thousands, they form crusts. Over hundreds of thousands, they become landscapes that shine. So, as you move south, in your mind, you start to see the future Salar de Uyuni, not as a tourist mirror, but as a mineral ledger. Each wet period expands lakes. Each dry period shrinks them. Each oscillation leaves shoreline marks, strand lines, terraces, rings on the basin walls. The plateau remembers climate shifts, the way a tree remembers drought in its rings. And those climate shifts are partly controlled by the plateau's own height. This is the feedback that makes the Altiplano feel inevitable. But it was not inevitable. It required a particular balance of uplift, thickening, and climate isolation. So you let your mind linger on an earlier Altiplano, lower and less harsh. You picture water behaving differently when the land is lower. You picture rivers that actually commit to a direction. You picture them leaving the basin, not just circling inside it like confused thoughts at 3 a.m. You picture a time when the eastern slope was not such a brutal squeeze point. You picture clouds making it farther west before they were wrung dry. And then you let that picture dissolve because the evidence on the ground refuses to cooperate. Look around, and the plateau is already acting like a sealed room. Not perfectly sealed, not forever sealed, but sealed enough that the salts have time to keep score. So, you do what you always do when a landscape lies with its calmness. You start hunting for the marks it could not hide. You follow the shore, not for the view, but for the small terraces. You look for old beaches, stranded above the modern waterline. You look for lines of rounded stones, sorted by waves that are no longer here. And when you find them, you feel the slow insult of time. Because strand lines mean lake levels changed, repeatedly, over and over. That is climate, yes. But it is also geometry. A basin only makes strand lines if it stays a basin long enough to fill and shrink again. You run your hand over the stones, and they are cold, and they do not care. They tell you the lake rose higher in the past. They also tell you the lake could not escape. So your next decision is simple and a little bleak. If the basin has no outlet now, you need to know when it lost it, or whether it ever had one at all. That question sends you away from the lake again. You walk inland, across ground that feels firm but gives slightly in places. You step over cracked mud and low tufts of grass and the occasional glitter of salt. Each crack is a tiny record of evaporation, a reminder that water leaves upward here, not downstream. You stop and listen. In the daytime, the Altiplano makes noise in a restrained way. Wind brushes stiff grass. A distant engine groans like it is offended by the grade. Somewhere, a bird calls once and then decides it has said enough. The quiet makes you aware of another thing. Your own body is still negotiating. Your breathing is louder than it should be. Your heart has decided to do extra shifts. Congratulations, you are learning that a plateau is not just a landform. It is a physiological policy. Now you tilt your attention to the east, because if moisture arrives from the Amazon, the eastern wall is where it gets processed. And processing is never gentle. You imagine the air mass coming in warm and wet. You imagine it sliding over lowlands, picking up heat and water like gossip. Then it meets the rising flank of the Andes, and it has to climb. Air does not climb because it is ambitious. It climbs because there is rock in the way. As it rises, it expands, it cools, and it loses its ability to hoard vapor. Clouds form fast, thick and bruised. Then the afternoon storms begin, the kind that feel personal. Rain hits the slope in sheets. Hail follows because the freezing level is uncomfortably close to the ground. Thunder bounces between ridges, and the mountains answer with rock falls. On that wet flank, rivers are not picturesque. They are contractors. They cut. They undercut. They destabilize slopes until gravity gets bored and pulls them down. Landslides happen the way paperwork happens, suddenly, and then all at once. And every ton of rock carried away is a ton of weight removed. That weight removal matters because the crust responds. Isostatic rebound, that yoga-sounding phrase, is the ground lifting as the load gets lighter. So the wet flank does not simply erode, it unloads the mountain belt, and the belt rises to compensate. You can feel the feedback like gears. Uplift makes slope. Slope makes erosion. Erosion removes mass. Removing mass makes uplift easier. The Andes, in a sense, are rising partly because they are being eaten. Now you shift your gaze westward again, back across the plateau, because the plateau is the shadow side of that storm machine. The air that survives the crossing descends. Descending air warms. Warming air dries. So the clouds thin and the rain gives up. On the Altiplano, the wet season is real, but it is rationed. The storms arrive smaller, more scattered, like they lost confidence. And the rivers, when they appear, behave like seasonal moods. They rush after a storm. They carry sediment like a panicked confession. Then they fade, leaving braided channels and damp sand that dries in hours. You squat beside one of these channels and you see how the story gets written. The gravel is poorly sorted, dumped quickly. The sand is fine, laid down in quieter moments. There are thin layers of silt that look like someone dusted the ground with flour. Each layer is a small flood, a small delivery. Add enough deliveries, and a basin fills. That is how a plateau gets flatter over time, even while the whole region rises. Sediment is the lazy assistant of tectonics. It smooths what compression roughens. Now you consider the other half of the plateau's climate machine. The West is not just dry because the East is wet. The West is also dry because the Pacific side has its own tricks. Cold ocean water, driven by currents, keeps the coastal air stable. Stable air does not like to rise. Air that does not rise does not like to rain. So the Pacific margin can be arid even though it is next to an ocean. Speaking of places that should not exist, you remember the Atacama, a desert so dry it sounds fictional, and you realize the Altiplano sits between two different kinds of dryness. One is created by rain shadow, the other is created by a cold sea and stubborn atmosphere. So your basin is pinched between stingy moisture sources, which is perfect if your goal is to preserve a high surface. It is less perfect if your goal is to live comfortably. You stand again, and the sunlight feels sharp on your face. Up here, the air is thinner and the ultraviolet is less filtered. You can feel it on your skin like an invisible sandpaper. Your lips dry, your eyes narrow. This is not just scenic altitude, it is exposure. Now you let the mind follow water south, because the plateau does not end at Titicaca. The Altiplano stretches, and the basins multiply. Some basins hold lakes, some hold seasonal wetlands, some hold nothing but salt and regret. As you drift southward in imagination, you pass through a geography of closure. Rivers begin confidently, then lose themselves. They spread into shallow fans. They sink into porous sediment. They evaporate. You watch a stream split into threads across a flat, and each thread dies quietly. No dramatic waterfall, no heroic canyon, just disappearance. And then, in the lowest parts, the water leaves behind what it carried. Salt is not introduced here by mystery. It is introduced by persistence. Every raindrop that falls on rock dissolves a little mineral. Every stream carries those minerals. In an open system, rivers export them to the sea. Here, the export is blocked, so the minerals stay and the only thing that leaves is the water itself. As vapor, that is how you build a salar. Slowly, patiently, ruthlessly, you kneel and touch a crust of salt. Thin in this spot, thicker elsewhere. It crunches softly. Underneath, the mud is dark and cold. The salt feels clean, but it is not purity. It is residue. It is what remains after the plateau refuses to drain. And when you lift your hand, a white dust clings to your skin, a small reminder that closed basins keep receipts. Now your mind pulls back to the bigger question again. How did this region get high enough to become a climate machine? You already have shortening. You already have thickening. You already have internal flow and sediment smoothing. But you also need timing, because climate feedbacks only amplify what tectonics initiates. So you start asking when the Altiplano reached the elevation where it could cast a serious rain shadow. And that is where the story stops being gradual, because some of the uplift may have come in pulses, not pulses you would feel in a lifetime. Pulses that still look sudden in the geologic record. You start thinking about what could cause a pulse. Not more compression, necessarily. Compression is steady, like a long argument. A pulse needs a structural change, something deep, something that changes buoyancy fast, something that removes weight from below. So you let the mind drop beneath the plateau again. Down past the cold surface, down past the brittle crust where earthquakes snap, down into the warm, ductile lower crust, then, deeper still, into the lithospheric mantle, the rigid part of the mantle attached to the plate. Under thick mountain belts, this lithosphere can grow a root, a keel, a deep extension of cold, dense material that helps support topography by isostasy. Like an iceberg, you rise higher when you have more volume below. But here is the problem. Not all roots are stable. Some roots become dense in the wrong way. As they cool and transform, minerals change. The word for one of those changes is eclogite, and it sounds like a niche perfume. It is actually basalt turning into something denser under pressure. Denser material wants to sink, and if you have a thickened root with patches that are too dense, you have a situation, a heavy underbelly, a continent wearing ankle weights. At first, it holds. It is attached. It is part of the system, but over time, heat rises into it, stress accumulates, and the attachment weakens. The root becomes a soggy ceiling, and you can feel the suspense because you know what ceilings do. They eventually choose gravity. You cannot see this from the surface, but the surface leaves hints. For one, volcanism can change character. If hot asthenosphere rises to replace a removed root, melting changes. Magmas can become different, hotter, sometimes more mafic. The volcanic arc can flare, not just because the slab supplies water, but because the mantle is suddenly closer and more available. For another hint, you see extension inside the plateau, normal faults, basin and range style structures. That seems wrong inside a compressional mountain belt. Wrong, unless the plateau has become so thick and high that it is spreading under its own weight, like a blob of dough flattening after you stop squeezing it. So you take those hints and you build a hypothesis you do not like. The Altiplano may have experienced episodes where its deep root detached. Delamination is the term, and it sounds surgical. because it is. Foundering is another term, and it sounds nautical because it is. Either way, the idea is the same. Part of the lower lithosphere peels off or drips down into the mantle. The heavy part leaves, and when the heavy part leaves, the remaining crust rebounds upward. Not instantly, but fast enough to matter in the landscape and climate record. So you stand again on the plateau surface, and you imagine the ground beneath you losing ballast. Imagine wearing a backpack filled with rocks. Now imagine the backpack strap snaps and the rocks fall away. Your shoulders rise. Your posture changes. You feel lighter. The plateau does the same thing, except the rocks fall into the mantle, and the posture change is 1,000 meters. That is not a metaphor your body enjoys, because 1,000 meters of uplift is a dramatic adjustment to air pressure, climate, and drainage. It turns a marginal rain shadow into a hard rain shadow. It turns lakes into salt factories. It turns a tolerable elevation into a place where visitors get headaches and locals get annoyed at them. So you need to see how this could be recorded. You start looking for the kinds of evidence geologists use when the Earth refuses to provide a timeline. You look at sediments in basins. If uplift accelerates, basins can tilt. Rivers can change direction. Lake deposits can shift from deep water clays to shallow water salts. You can see that in the layers, like a diary. You look at fossil pollen, telling you what plants could survive, which tells you about moisture. You look at isotopes in carbonates, oxygen isotopes in ancient lake beds, the chemical signature of evaporation versus rainfall. You look at volcanic ash layers, because ash can be dated. And between those dated layers, you see changes in sediment type, a shift from fluvial deposits to more evaporitic deposits, a shift from connected drainage to internal drainage. These are not perfect records, but they are suggestive. They whisper that something changed in the plateau's elevation and aridity. Now you make another decision. You stop thinking of uplift as a smooth ramp. You think of it as a staircase. Long periods of slow rise, then a step when deep structure changes. Then another long period. That staircase model fits a plateau that becomes more self-reinforcing over time. Because once the plateau crosses certain thresholds, climate feedbacks lock in. More height, stronger shadow, less erosion inside. Less erosion inside, flatter surface persists. Flatter surface, drainage stays internal. Internal drainage, more salts, more bright surfaces that reflect sunlight, changing local energy balance. Even the surface color can feed back slightly into temperature and evaporation. It is all connected. Because of course it is. Earth loves a system. Now, before you let the deep horror of delamination take over, you need to finish the climate chapter properly. Because climate is not only rain shadows, it is also oscillation. The plateau sits in a region influenced by changes in global circulation, glacial periods, interglacial periods, shifts in the position of tropical rainfall belts, changes in the strength of monsoonal flow from the east. During wetter periods, paleolakes expand. They connect basins that are separate today. They turn salt flats into shallow seas. During drier periods, those lakes collapse. They leave salts exposed to wind. The wind picks up dust, and the dust goes somewhere else, sometimes fertilizing distant ecosystems. So the plateau is not just passively dry, it breathes with climate cycles. You can see the breath in high shoreline terraces around basins. You can see it in lakebed sequences. You can see it in the fact that the Salar de Uyuni, when flooded, becomes a mirror so perfect it looks like the sky fell and decided to stay. But you also see it in the cracks when it dries, polygons of salt, fractures that widen, then heal, then widen again. The surface is calm only when you do not look closely. So you take a slow walk across an imagined salar at dusk. The light is low, the horizon is level. Your footsteps crunch. Each crunch is salt breaking, and it sounds delicate, but it is not. It is a crust thickened by thousands of years of concentrated loss. The air is so dry, your throat feels like paper, and the wind is steady, moving across the flats as if it has a schedule. This is where the Plateau's climate story ends up, in a place where water becomes absence made visible. Now, you pull the camera of your mind back toward the mountains again, because the plateau does not exist as a simple flat. It is framed, it is held, and those frames are being eroded and uplifted at different rates. The Eastern Cordillera is carved by wet rivers. The Western Cordillera is marked by volcanoes and arid slopes. In the middle, the Altiplano collects sediment and maintains broad elevation. That asymmetry matters, because erosion on one side can focus uplift there. It can also shift where deformation occurs. There is a concept called orogenic wedge, and it describes how a mountain belt maintains a certain shape under compression. If one side erodes faster, the wedge can adjust. Faults can activate differently. The belt can migrate. So climate is not only shaping the surface, it is influencing the internal structure indirectly by changing loads. You imagine the Andes as a wedge being pushed. You imagine it like a snowplow pushing snow. If the snow is removed from one side faster, the pile shifts. It is crude, but it works. And over millions of years, crude mechanics produce elegant topography. Now you feel the story tightening again, because you have a thickened crust, a climate machine, and a basin system that stores sediment and salt. That is already enough to make the Altiplano feel like a stable feature. But then you remember the warning you gave yourself earlier. Thickening has a limit. Roots can become unstable. And when roots become unstable, the change is not reversible. Once you drop dense lithosphere into the mantle, you do not just glue it back. The system has crossed a line. So you let the mind sink down again, deeper than comfort. You picture the crustal root beneath the plateau. It is thick, but it is not uniform. Some parts are hotter, some are colder, some are compositionally different, depending on what rocks were underplated, intruded, or transformed. Heat from magma intrusions can weaken the lower crust. Pressure can transform minerals into denser forms, and if the root becomes both heavy and weak, it starts to behave like a drip, a slow sag, a downward finger of dense material extending into the mantle. At first, it is small. It does not matter at the surface. Then it grows. It pulls down on the lithosphere above. Subtly, it changes stress patterns. It may create subsidence in basins. And then, one day in geologic time, it detaches. The dense root segment drops. It sinks because it is heavier than the surrounding mantle. It falls not like a rock in water, but like cold honey through warm honey. Slow, unstoppable, and still fast enough to matter. And when it leaves, the buoyancy balance changes. The remaining crust rises. The plateau steps upward. That step may happen over a few million years, which, for a continent, is basically an impulsive decision. Now you follow the chain reaction. When the root drops away, hot asthenosphere rises to fill the space. That asthenosphere is warmer than the lithosphere it replaces. Warmer material means more melt potential, especially if fluids are present from subduction. So volcanism can intensify, not necessarily everywhere, not neatly, but enough to leave a signature. You can get ignimbrites, huge sheets of welded volcanic ash from explosive eruptions. You can get calderas, collapsed volcano tops after magma chambers empty. You can get a volcanic plateau overlaying parts of the older surface, like fresh paint. That is also toxic. At the same time, the uplift changes the stress field. Faults can reactivate. Some thrust faults may slow. Normal faults may appear within the plateau because gravitational potential energy is now higher. A thick, high plateau wants to spread, so you get extension, rifting tendencies, basins dropping down along normal faults. Inside a mountain belt that is still under compression at the margins, you get internal stretching. Geography loves contradictions. Now you need to see how that looks from the surface. You stand, in your mind, at the edge of a fault-bounded basin on the Altiplano. The basin floor is flat, filled with sediments. The basin margins are straight, abrupt, like someone cut the landscape with a knife. Those straight margins are fault scarps, normal faults, where one block dropped relative to the other. You walk toward the scarp, and the ground underfoot changes. Loose sediment near the basin center, coarser debris near the margin. A fan of gravel spreading out from a canyon mouth, dumped by rare but violent floods. Each fan is a reminder that when rain does come, it arrives with impatience. You look up at the scarp, and you imagine the earthquake that moved it. The scarp does not look like much until you imagine it moving. A clean line in dirt becomes a moment when the ground forgets its job. Some night, the basin floor dropped a little, and nobody asked your permission. And in the morning, the same flatness that comforts you also hides the damage. You walk closer because distance makes hazards feel polite. Up close, you see the slope is made of loose, angular fragments. These are not river-rounded stones. They are freshly broken pieces. They tumbled down after shaking, after gravity got invited to the party. You run your glove along the face, and the material comes away like dry sugar. This is the penalty of a high, dry place. When something breaks, it stays broken. There is not enough rain here to blur the scar quickly, so faults become long memories on the surface. And this is your next revelation. The plateau is not only lifted by compression, it is also being stretched apart from within. Congratulations. You found extension inside a mountain belt. It sounds like a contradiction until you remember the plateau's weight. A thick crust holds enormous gravitational potential energy. That is a technical phrase for a simple feeling. Everything up here wants to slide downhill. Even rock, even continents. So while the Nazca Plate keeps shoving from the west, the plateau spreads like a heavy blanket. The margins crumple, and the interior tears in slow motion. You step back from the scarp, and you try to picture the forces together. Compression at the edges, thickening the crust. A hot, weak lower crust flowing sideways like warmed wax. a high surface, loading itself, then relaxing outward by faulting. And somewhere deep below, a missing chunk of lithosphere, already sunk. This is not one mechanism. This is a system with competing urges. Now you make a decision because the landscape has given you a clue and a demand. If extension is real here, you want to know what triggered it. Was it simply the plateau getting high enough? Or did the deep root removal change the rules suddenly? So you start looking for timing, because timing is where stories stop being poetry. You cannot date a fault scarp with your eyes, but you can read the layers that the fault slices through. In these basins, sediment accumulates like sleepy paperwork. Alluvial fans, lake muds, volcanic ash, more fans, more muds. If the fault cuts young layers, the extension is young. If it cuts only old layers, the tearing happened earlier. So you imagine drilling down through the basin fill, not because you want to, but because this is what the evidence requires. At the top, loose gravel, dumped by recent storms. Below that, finer silts, deposited when the basin held shallow water. Below that, an ash layer, pale and sharp, a timestamp from an eruption. Below that, older lake clays, darker, more organic, from a wetter interval. And somewhere in that stack, you see offsets. Layers that used to line up are now stepped. That step is a fault slip recorded like a misprinted page. In places, you get repeated offsets, multiple earthquakes, a long argument with gravity. This is how you know the plateau is still adjusting. Not because of one ancient uplift event, but because the deep engine is still running. Now you follow another thread of evidence, because faults are not the only things that respond to root loss. Heat does too. When dense lithosphere detaches, hot asthenosphere rises. Hotter mantle means more melting potential. More melt means more volcanoes, or at least more enthusiastic ones. So you turn your attention westward again, toward the volcanic arc. You travel across a plain that looks empty from far away. Then you realize the emptiness is made of details: pumice, ash, lava rubble, wind-polished stones. The ground is a palimpsest of eruptions, not one volcano, but a province of vents and scars, and the air carries a faint mineral tang, like wet matches even when it is dry. You approach a volcanic cone at dusk, when the shadows make everything look more serious. The slope is built from loose cinders, black and red, crunching underfoot. You take 2 steps and slide one back. It is a hill made of broken glass and burned rock, and it reminds you of the mantle wedge plumbing you traced earlier. Water leaves the slab, melts rise, and the crust becomes a complicated filter. Some melts stall, cooling into intrusive bodies that heat the crust for millions of years. Some reach the surface and explode because gas expands violently at low pressure. On a high plateau, pressure is already lower. That matters. Magma ascending here has less atmospheric weight holding it down. Gases expand earlier, faster, and eruptions can become more explosive. So altitude is not just a human problem. It changes volcanic behavior too. You circle the cone and you look for layers. A band of ash, then a band of scoria, then a thin lava flow. Each layer is a different mood of the same volcano, and in the distance, you see something wider. Not a cone, but a collapsed depression, a caldera, a place where the roof fell in after the magma chamber emptied. From above, it would look like a ring. From here, it looks like a missing piece of the world. Calderas are not just holes. They are evidence of large magma volumes moving through the crust. And large volumes are easier to explain if you have extra heat rising from below. So delamination does not only lift the plateau, it can also feed the volcanic appetite. Now you pause, because you need a reality check again. Volcanoes on documentaries always look noble. In real life, they are bureaucrats of inconvenience. Ash clogs lungs, kills crops, collapses roofs, ruins engines. It turns snowfields into dirty heat absorbers, speeding melt. It makes water taste like a chemistry set. On the plateau, where water is already rationed, ash is not dramatic. It is catastrophic in slow motion. You imagine a town downwind of an eruption, adobe walls turning gray, fields buried in a thin, abrasive layer, livestock coughing, people sweeping ash from doorways, knowing it will return with the wind. And you understand the plateau's human penalty as layered. Thin air, cold nights, scarce water, unstable ground, and occasional sky dust. Congratulations, you live on a high table that can shake and burn. Now you make another decision, because volcanoes are a spectacle, but faults are a habit. You want to feel the plateau's internal spreading more directly. So you find a basin that is clearly extensional, a long, flat trough bounded by faults. In the central Andes, these basins have names that sound like they were spoken into cold wind. They hold towns, because humans prefer flat ground even when it is a trap. They hold farmland, because sediment is fertile when you can water it. They hold roads, because building on slopes is expensive, and everyone is tired. You walk into one of these basins in your mind. Late afternoon. The basin floor is broad and deceptively calm. A river threads through it, shallow, braided, changing channels like it cannot commit. On the margins, the fault scarps rise in straight lines. The geometry is too clean to be natural erosion. This is tectonics doing carpentry. You stand on the basin floor and look back at the scarp. You imagine the block on this side dropping, millimeter by millimeter, quake by quake. And now you feel the plateau's paradox in your bones. The whole region rose because of compression and buoyancy. But inside, it is failing in extension because it is too high and too thick. This is not collapse in the sense of mountains disappearing overnight. It is gravitational spreading, slow but persistent. The plateau is trying to become less extreme. The margins are still being shoved, so it compromises by cracking. Now you follow the river because water is the only thing that makes decisions faster than rock. The channel carries meltwater in some seasons. It carries storm runoff in others. It also carries silt, and that silt is the basin's quiet architect. You watch how the river loses itself into sediment. In places, it sinks into the ground and reappears downstream. That tells you the basin fill is porous, like a sponge. It also tells you groundwater matters here more than surface water. And groundwater in an extensional basin is vulnerable. Faults can act like barriers or like conduits. They can trap water on one side or drain it deeper. So the tectonics does not only shape hills, it controls wells. Now you picture a farmer here, not romantic, just practical. They dig canals, shallow and temporary. They divert water when it exists. then watch it vanish into soil. They gamble on timing. Too early, and frost kills seedlings. Too late, and rains never arrive. And above them, the plateau watches. Indifferent. The farmer's schedule is seasonal. The plateau's schedule is tectonic. They do not align. Now you return to the deep mechanism again, because the mid-story hinge is delamination, and you have circled it. You need to make it feel real, not just conceptual, so you drop your imagination beneath the basin floor. You pass through sediment, then brittle crust. You enter the ductile lower crust, where rocks are warmer and weaker. Here, deformation is not a snap, it is a smear. A shear zone is not a single break, it is a band of rock that has been kneaded until its minerals align like stretched taffy. And below that, you reach the mantle lithosphere that used to be the plateau's root. You picture it as cold and dense, a keel. But time and chemistry have changed parts of it. Some basaltic material, underplated or dragged down, transformed into eclogite. Eclogite is heavier and it does not want to float. So the root becomes a mixed structure, some buoyant, some too dense. That density contrast is an instability. And instability on a planet with gravity is a promise. You picture the root starting to drip, not a dramatic tear at first, a slow necking, a thinning zone where the root is being pulled downward. The mantle around it flows, because mantle always flows. That flow can focus the drip, stretching it like a candle wax stalactite. Then, when it thins enough, it detaches. The heavy piece drops. The word foundering finally feels appropriate. It sinks, taking its weight with it, and above, the plateau rebounds. But rebound is not only vertical, the thermal structure changes. Hot asthenosphere rises, heating the base of the crust. That heating lowers viscosity, making lower crustal flow easier. So after delamination, the plateau is more prone to internal spreading. Faults become more active. Basins open more readily. Volcanism can flare, and the climate consequences intensify, because even a few hundred meters of extra elevation changes moisture transport. This is why delamination is a pivot. It does not just lift land, it reorganizes the system. Now you bring in the kind of evidence that makes this less of a ghost story. Geochemists look at volcanic rocks. They measure isotopes, trace elements, ratios that behave differently depending on the source. Arc magmas, influenced by subducted slab fluids, have a certain fingerprint. Magmas influenced by rising asthenosphere, with less slab signature, can look different. If the plateau experienced delamination, you might see a change in volcanic chemistry over time. You might see more mafic compositions appearing in pulses. You might see ignimbrite flare-ups, huge explosive events. And in the central Andes, there are ignimbrite sheets that cover enormous areas. They are like ash blankets welded by their own heat. They tell you that at times, the system produced magma volumes that are difficult to explain with steady subduction alone. It suggests extra heat, extra melt, extra capacity. That is consistent with lithospheric removal, not proven by one line of evidence, but supported by a chorus. Now you widen the view again, because you cannot understand the Altiplano from one basin. You need to feel the plateau as a whole, behaving like a living object, so you stand at night on a ridge above the plain. The air is so dry that the stars look close, sharp, almost rude. The temperature drops quickly after sunset. Your breath becomes visible, then disappears because the wind steals it. In the distance, lights from a town flicker, small, concentrated, as if humans are trying to stay together for warmth. You look across the plateau surface and it seems calm. But you know there are microquakes. You know GPS stations measure motion in millimeters per year. You know faults are creeping or locking. You know magma is cooling somewhere beneath a caldera or rising slowly toward a vent. So the calmness is only visual. The plateau is alive in the slowest way. Now you let yourself notice the body feeling again, because this story is second person and your lungs demand inclusion. Your head aches faintly. Not enough to panic, just enough to make you aware of your skull. That ache is a reminder that Uplift changes everything living here. It also forces human adaptation into strange places. People chew coca leaves, not as a cliché, but as a tool. They build houses with thick walls to buffer temperature swings. They time travel by season, moving herds to different grazing zones. They respect water sources like sacred infrastructure. And in cities like La Paz and El Alto, people build on steep, unstable slopes because the flat plateau is already crowded. The plateau's geometry forces social geometry. Now you shift back toward a specific hazard because the plateau's human penalty is not theoretical. It is infrastructure. When a basin tilts slightly after faulting, drainage patterns change. A canal that used to flow no longer does. A lake shoreline moves, exposing mud or flooding fields. Roads crack, pipelines strain. Buildings settle unevenly on sediment that compacts or liquefies during shaking. So, when you imagine an earthquake here, you imagine it as a bureaucratic disaster. Not one big collapse, but thousands of small failures. And because the air is thin and resources are limited, recovery costs more. Geology does not just shape landscapes, it shapes budgets. And now you move, because staying in hazard mode too long becomes noise. You need the next bridge in the outline. You have reached the chapter where the plateau vents and cracks under its new weight. You have seen volcanoes and faults. Now you need to understand how those features keep the plateau going, not just how they punish it. So, you follow heat. You find a geothermal area because the Andes is full of them. Steam rises from vents in the ground in the cold morning. The smell is sulfur, sharp and unmistakable. It is the scent of deep chemistry meeting surface air. Pools of water bubble, tinted with minerals. The ground around them is stained yellow, orange, white. It looks like spilled paint, but it is a warning. Thin crust, high heat flow, active magmatism, and faults that provide pathways. That is the recipe for geothermal activity. And geothermal activity tells you the crust is not just thick. It is warm. Warm enough to be weak at depth, weak enough to flow. So, geothermal vents are not only curiosities, they are surface hints of the deep ductile behavior that made the plateau broad. Now, you pay attention to the water itself. On the plateau, groundwater is often old. It may have infiltrated during wetter climate periods. It may have moved slowly through basin fill. It picks up dissolved minerals, and when it emerges, it deposits them. Travertine terraces can form, layered calcium carbonate. Step by step, those terraces are small landscapes, mini plateaus on the plateau. They tell you water chemistry and flow persisted long enough to build structure, and persistence is the plateau's theme. Everything here is about things happening long enough to matter. Now you pivot again, because the volcanic arc is not only cones, it is also broad ignimbrite plateaus and ash plains. So you travel across one where the ground is pale and soft, made of welded tuff. It looks like compacted dust, but it is solid enough to form cliffs. Wind has carved small hollows, undercutting softer layers. In places, the rock breaks into blocks with sharp edges. You touch one and it feels light for stone, porous. That porosity matters. It stores water briefly, then gives it up to evaporation. It weathers into fine dust that the wind can carry. So volcanism feeds the plateau's dust cycle, and dust feeds climate in subtle ways, reflecting sunlight, seeding clouds, fertilizing distant soils. Even the plateau's emptiness has consequences beyond itself. Now you check yourself because you have drifted into complexity again. So you bring it back to a simple chain. Subduction compresses and thickens crust. Thick crust creates high elevation and a rain shadow. High elevation and thick crust become unstable in places. Instability leads to delamination and foundering. Delamination triggers uplift pulses, more heat and volcanism. Heat and high gravitational potential energy encourage extension within the plateau. Extension creates basins that trap sediment and water. Trapped water evaporates, leaving salt, reinforcing internal drainage. Internal drainage and dryness preserve flatness. Flatness makes humans settle because humans love easy building sites. And settlement increases the cost of the next quake or eruption. That is the plateau as a machine. Not one cause, but many linked consequences. Now the story wants to return to the deceptively calm flats, because after volcanoes and scarps, you need the eerie quiet of the Salar again. You move south in your mind toward Salar de Uyuni. You arrive near evening, when the light turns low and the horizon becomes a razor. The Salar stretches outward, a white expanse that looks like snow, without the kindness. If there is a thin film of water, it becomes a mirror, sky above, sky below, and you standing in between like a mistake. If it is dry, the surface is a mosaic of polygons, cracked plates of salt, edges raised, centers sunken. It looks like reptile skin on a planetary scale. You step onto it carefully. The crust holds, then crunches. Underneath is brine and mud, and in places, a softness that could swallow a boot. The Salar is flat, but it is not safe. Flatness is not the same as stability. You walk farther out, and the wind has nothing to interrupt it. It moves across the salt and makes a faint hiss. It is the sound of abrasion, of crystals rubbing, of the air practicing erosion. And here comes the next reveal. This stillness is cosmetic. The plateau is not finished. It is still moving, still adjusting, still being shoved from the west. Even here, on the flattest surface you can imagine, motion continues. Now you decide to audit that motion. because the outline demands aftermath in deep time. So you become a forensic accountant of landscapes. You look for strand lines. On the basin margins, faint terraces climb the slopes. Old shorelines, some subtle, some clear. They sit far above any modern water. They tell you paleo lakes once filled this basin deeply, not once, but many times. The lakes had names in the scientific literature, like ancient ghosts, lakes that expanded during wetter periods, connecting basins, then shrank, leaving salt. So the salar is not a lake bed from one event. It is the residue of repeated filling and dying. You pick up a chunk of salt, and it is layered. Thin bands, slightly different colors. Each band is a change in chemistry, in water depth, in evaporation rate. The salar is stratified time. Now you look for ash layers. In some exposures on basin edges, you see thin, pale bands in darker sediment. Those are tephra, volcanic ash deposits. They can be dated. They allow you to tie lake level changes to specific time windows. So you pick a cut bank where the wind has exposed a clean slice of sediment. You run your glove along it, and the grains cling like powdered history. You can see the lake beds alternating with dry spells, like the basin kept changing its mind. One layer is fine mud, settled in quiet water, patient and dark. Another is chalky and pale, a crust that only forms when water evaporates to nothing. Then an ash band slices through them, thin as a bad excuse, and suddenly you have a clock. Now you can ask a sharper question. Did the lake changes happen only because climate pulsed? Or because the ground itself lifted or tilted? You do not get to choose. One, because the Altiplano refuses to be simple. So, you follow the evidence the way the Plateau forces you to, sideways and reluctantly. You walk the basin margin looking for the same ash layer at different elevations. You find it again, a pale seam in a different outcrop, meters higher than it should be. You feel a small chill, and not from the wind, because if the same time marker sits at different heights, something moved after it fell. Either the basin tilted, or faults offset the layers, or uplift warped the surface. Congratulations. You just caught the Plateau cheating, moving the goalpost after the fact. Now you zoom out, because a single outcrop is a whisper. You need the whole basin to speak. You imagine flying above Salar de Uyuni, not as a tourist drone, but as a suspicious auditor. The flats are level, but the margins are not perfectly symmetric. One side has broader fans, thicker sediment aprons, a different slope angle. That asymmetry is not aesthetics. That is structure, faulting and flexing, the basin being gently tortured. You focus on the fans spilling out of the surrounding hills. Each fan is a pile of debris that arrived in bursts when storms got serious. The fans build outward, then stop, then build again. Like the mountains keep shedding, and the mountains shed faster when uplift steepens them. So the fans are not only climate products, they are uplift products, translated into gravel. You walk onto one of these fans in your mind, and the stones underfoot are sharp. They have not traveled far enough to be rounded into politeness. This is local destruction, nearby cliffs breaking, nearby channels dumping. And that tells you the basin rim is still rising and cracking. Now, you shift attention to the center of the salar. The surface looks like a perfect plane. but beneath it is a stack, salt crust above, then muddy brine layers, then older muds, then older salts. Each layer is a lake that lived briefly and died slowly. And that stack is heavy, so heavy that it makes the crust bend a little under it, which means the basin can create its own subsidence even while the plateau rises overall. This is what makes the Altiplano so irritating. To summarize, everything happens at once and none of it cancels the rest. Now you decide to trace motion in the present because the outline demands you face the fact that it is not over. So you imagine a small metal post drilled into bedrock near the basin edge, a global positioning system station, blinking quietly into the cold. It does not care about legends or salt mirrors or your sleep. It just counts millimeters. Day after day, it watches the plateau inch, not in one direction, but in a messy vector. A little shortening here, a little extension there, a little uplift, a little subsidence. The numbers are small enough to insult you, but the time span is huge enough to win. Now you connect those millimeters back to the trench, because the Nazca Plate is still diving, still hydrated, still dragging its history under the continent. Subduction does not stop because the surface looks calm. The trench keeps pulling like a slow zipper, and every year the continent has to decide where to store that strain. Sometimes it stores it as earthquakes along the interface. Sometimes it stores it as folding and thrusting at the margins. Sometimes it stores it as extension inside the plateau, because the plateau is too high to behave. So you stand on salt that looks dead, and you realize you are standing on an argument between pushing and spreading, between thickening and erosion, between water trying to carve an exit and rims that refuse to lower. Now you let yourself feel the stillness again, because it is part of the trap. Wind moves across the flats, steady and dry, and it feels like the world is holding its breath. But the basin edges show old shorelines, and those shorelines are perched like scars. Some are subtle gravel lines, others are full terraces, wave-cut steps on the hills. They sit, one above another, not random, but grouped. Clusters of shorelines, like the lake stabilized at certain levels for a while, then jumped, then stabilized again. That kind of stepping can come from climate. It can also come from tectonics changing basin geometry. If uplift tilts the basin, the lake level relative to the rim changes. If faulting drops one margin, water deepens there. If uplift raises the outlet threshold, the basin becomes more closed. So you stop thinking of the Salar as a dead end. You think of it as a gauge, measuring the balance between climate input and tectonic containment. Now you decide to test the containment idea in your mind. You trace hypothetical water paths during a wet period. Rain and meltwater runoff surrounding volcanoes and ranges. Streams converge toward the low interior, feeding a broad paleo lake. The lake expands until it reaches a spill point, the lowest notch in the rim. If it spills, it becomes an open basin and salts flush out. If it does not spill, evaporation concentrates salts and the Salar thickens. So the entire chemical fate of this place depends on a few low saddles in the rim, a few pieces of topography controlled by faults and uplift. This is not romantic. This is plumbing with continental scale consequences. Now you let the mind drift north for a moment to Lake Titicaca again. Not to repeat it, but to compare. Titicaca is high, but it is fresher, less salty, because it has a partial outlet. It sits in a different basin configuration, different thresholds, different history. Uyuni is more terminal, more punitive, more efficient at turning water into crust. So you realize the Altiplano is not one basin. It is a patchwork of basins, each with its own rules, each reacting to uplift in climate. Some basins are more open in wet times. Some are permanently closed. Some switch, depending on how the plateau tilts, and tilting can come from faults or from broad warping as the crust adjusts. Now you return to the deep time consequences, because the outline demands you face persistence. The plateau persists because the engine persists. But persistence does not mean stability. It means ongoing negotiation with occasional tantrums. So you start listing the tantrums the plateau is capable of. A big interface earthquake at the coast, shaking cities, lifting terraces. A crustal earthquake within the plateau, dropping a basin margin by a step. A caldera eruption, laying down ash over hundreds of kilometers. A shift in the slab angle, changing where deformation concentrates. Another delamination event if the lithosphere thickens again and becomes unstable. And then the quieter tantrums, the ones that hurt slowly. A multi-year drought, shrinking lakes, exposing salt, raising dust. A wet interval, expanding lakes, flooding low areas, changing salinity. A glacial advance in the high Cordilleras, storing water as ice. A glacial retreat, releasing meltwater briefly, then leaving nothing. Now you realize how cruel the plateau is about timing. It gives water when it is cold and takes it when it is warm. It gives flat ground, then shakes it. It gives mineral wealth, then buries it under brine. It gives spectacular skies, then punishes your lungs for looking up. Congratulations. You are living on a compromise, and compromises always need maintenance. Now you choose a new piece of evidence because you need more than shorelines and ash. You look for microquakes, the tiny tremors that never make headlines. They cluster along faults, along old scars, along the margins of basins. Some cluster beneath volcanoes, where magma is moving, cracking rock. Some cluster deeper, where the crust is adjusting to stress. These microquakes are the plateau talking in its sleep. Small pops and creaks in a structure that is too heavy to relax quietly. And the pattern matters. If quakes align with normal faults, extension is active. If they align with thrusts, compression is still winning in places. If they align in swarms under a volcano, heat is still rising. So even without a single dramatic event, the plateau proves it is not finished. Now you decide to connect that to the human scale again. Because a living plateau means living with uncertainty. You picture a road across the Salar, straight and tempting. It looks like the easiest route on Earth. But in wet season, a thin film of water hides soft mud beneath crust. Vehicles bob down, and the flats become a slow trap. On basin margins, towns sit on sediments that amplify shaking. On alluvial fans, channels can jump during rare floods. On volcanic slopes, ash layers can fail as debris flows when rain finally commits. So the flatness that humans love is often the flatness that betrays them. Now you let the night return because the story is supposed to lull you, even when it threatens you. The salar under starlight looks like a frozen sea. The salt crystals sparkle, tiny reflections, like the ground has its own sky. The air is cold enough to make your nostrils sting, and the silence is so wide that you can hear your clothing move. This is when the philosophical pivot arrives, whether you want it or not. Because standing on a surface that is both ancient and temporary does something to your brain. It makes your schedule feel embarrassing. The plateau took tens of millions of years to rise, and it is still rising, still being remodeled. Your life is a blink. Your problems are weather. The crust does not care. And that indifference is oddly calming once you stop taking it personally. Now you make a decision that feels small, but matters. You decide to walk toward the basin margin, toward one of the low hills where strand lines climb, because you want to see how far above modern water those ancient levels sit. You climb slowly, because altitude makes even walking feel like paperwork. The slope is gentle at first, then steeper. The salt glare fades behind you, replaced by dusty gravel and sparse tufts of grass. Halfway up, you find a clear shoreline bench, a flat step cut into the hillside with rounded stones sorted by waves. You stand on it, and you look out across the salar. From here, the flat looks even flatter, and you realize this bench is a memory of depth. At the time this bench formed, water stretched to your feet. The basin was a lake big enough to have waves, big enough to carve steps. Now that water is gone, but the step remains. So you keep climbing, you find another bench above it, and another. Each one is a different lake stand, a different climate moment, or a different basin geometry, and the spacing between them tells you something else. Some benches are close together, like the lake hovered. Others are far apart, like the system shifted more dramatically. That dramatic spacing is where you suspect tectonics leaned on the scale. Now you pause and look at the surrounding highlands. Volcanoes on the horizon, their silhouettes clean in the thin air. Vaulted ranges, straight-edged, notched like broken teeth. And you remember that the plateau is boxed in by these rims. So you start seeing the benches not only as climate marks, but as a record of rim control. Because the lake level cannot exceed the lowest rim point. So if the benches represent stable lake levels, they represent stable rim thresholds. And stable thresholds imply the rim was not being lowered by erosion fast enough, meaning uplift and aridity preserved it. So the lake history confirms the bigger story. The plateau rose, it dried, it trapped water, it made salt. Then it kept rising and adjusting, and the lakes kept rewriting their edges. Now you decide to take the story below ground again, but gently. Because the aftermath chapter is not only about motion, it is about why nothing settles, why the plateau cannot become finished. The simplest reason is that the driver keeps pushing. As long as the Nazca plate subducts, compression and magmatism continue. But there is a second reason. Quieter. A thick plateau is mechanically restless. It stores gravitational potential energy like a wound stores tension. Even if subduction stopped tomorrow, the plateau would still spread for a long time. The lower crust, warm and weak, would keep flowing. Normal faults would keep adjusting basin floors. Rivers would keep trying to find an outlet, and failing and trying again. So the Altiplano is not a landform you complete. It is a state the continent is in, like a long fever. Now you decide to examine another kind of record, because shorelines and ash are not the only archive. You imagine a core drilled from the salar, a cylinder of sediment pulled up, wet and heavy, smelling faintly of minerals. In that core, layers alternate: dark, organic, rich mud from wet times when algae bloomed, light evaporites from dry times when salt precipitated, thin ash bands, timestamps again, and trapped gases and isotopes that reveal evaporation intensity. This core is like a sleep study for the plateau. It tells you when it breathed wet air. It tells you when it exhaled water into the sky. And it tells you that the pattern is not steady. It is cyclical, but the cycles change because the plateau itself changes. As elevation rises, evaporation increases. As rain shadows strengthen, inflow decreases. As basins tilt, shoreline geometry shifts. So the same global climate cycle can produce different local outcomes through time. This is how you know uplift mattered. The plateau became a different machine as it rose. Now you bring in one more modern annoyance, because anachronistic analogies keep you awake. Think of the Altiplano like a giant rooftop. At first, the roof is low enough that rain can still wash things off. Then the roof rises, and the gutters stop working. Water still falls, but it pools. Leaves and dust collect. Then someone adds another layer of insulation underneath, and the roof bows. Then part of the underlayer falls out, and the roof pops upward, cracking tiles. Now the roof is higher, flatter, and more prone to weird puddles. That is basically what the continent did, except with rock, heat, and 10 million years. Now you step down from the hillside bench and return toward the flats. Your legs feel heavy because altitude is not impressed by your curiosity. The cold comes up from the salt like it is radiating from a refrigerator floor. You walk across polygon cracks again, each edge slightly raised, like the crust is curling. Those curls form because salt expands and contracts with temperature and moisture. Daily cycles, seasonal cycles, all leaving texture. Even without tectonics, the surface is always moving. So the plateau has motion at every scale. Crystals shifting underfoot, dust lifting into wind, water evaporating invisibly, faults slipping in rare jerks, plates grinding for millions of years. Now you decide to listen again, because sound matters in the quiet. Far away, you hear a faint engine, a truck crossing the flats, chasing a straight line. The sound carries strangely, unobstructed by trees or buildings. It feels like the plateau is amplifying it, like a drumhead. And that drumhead image is appropriate, because a thick crust can resonate during earthquakes. Sediment-filled basins can trap seismic waves and amplify shaking. So even the way sound travels hints at what the ground will do when it is jolted. Now you pivot to the margins again, because the plateau does not exist without its rims. The rims are where erosion and uplift fight most visibly. On the eastern side, rivers still cut aggressively, dragging sediment down toward the lowlands. On the western side, aridity preserves volcanic slopes, but wind erosion is relentless. So the plateau is being trimmed at the edges, even as it persists. And trimming matters, because unloading at the margins can encourage uplift. Remove weight, the crust rebounds. So erosion is still a partner in keeping the plateau high. It is a partner that destroys, and in destroying, it sustains. Now you make a decision that feels like a bridge to what comes next. You decide to imagine the plateau not in the present, but a few million years forward. Not because you can predict, but because you can follow tendencies. If subduction continues at a similar pace, compression persists. Crust may thicken more in some sectors, but the plateau is already thick, already high. So additional thickening increases instability. That means extension inside may intensify, making more fault-bounded basins. Volcanism may migrate or flare depending on slab geometry. And if the deep lithosphere regrows and becomes dense again, another delamination could occur, another uplift pulse, another rearrangement. So the future is not a single direction. It is a set of repeating options, chosen by deep mechanics. Now you pull back from prediction, because prediction is a good way to get humbled. Instead, you focus on what is certain. The Nazca plate will keep diving until something changes at plate scale. The trench will keep eating seafloor. The continent will keep shortening and thickening in some zones. The plateau will keep spreading internally because it is heavy. Climate will keep oscillating, shifting lake levels, salinity, dust, and humans will keep building on the flattest surfaces because they always do. So the costs will keep appearing in different forms. Now you return one more time to the idea of the plateau as a process. It is tempting to say the Altiplano was created, as if it is finished. But standing here, you feel how wrong that is. The salt under your boots is temporary. It dissolves and recrystallizes. The basins are temporary, they drop and fill. The volcanoes are temporary, they build and collapse. Even the plateau elevation is temporary, held by a balance that can change. So creation is the wrong verb. The plateau is being negotiated continuously. Now you decide to collect the threads again, because sleepiness likes coherence. Subduction supplies compression and fluids. Compression thickens crust across a wide zone. Thick crust floats high, creating a broad, elevated interior. Deep heat weakens the lower crust, allowing flow that smooths topography. Rising elevation reorganizes climate, strengthening rain shadows. Rain shadows trap drainage, turning basins endorheic, closed and salty. Sediment fills lows, flattening the surface further. Thickened lithosphere can become unstable, delaminating, causing uplift pulses and extra heat. Extra heat fuels volcanism and weakens the crust, encouraging extension within the plateau. Extension forms more basins, which trap more sediment and water. And the cycle continues, not as a loop, but as a tendency. Now you let your attention drift toward the plateau rim again, because you need a place to stand that feels like an edge. You approach a low escarpment where the salar gives way to gravel plains. The ground rises slightly and the salt glare softens. From this edge, you can see the basin as a whole, a white center, darker margins, mountains, holding it like a shallow bowl. And you realize the bowl itself is the real artifact, not the water, not the salt, not the sky reflections. The bowl is what tectonics built. a high bowl perched near the roof of the continent. Now you wait there,